Welcome and thank you for joining. My name is Hugo Castro. I am head of the Project Execution and Delivery Division of ETAP. Today, I will be presenting the ETAP Intelligent Load Sharing System, ILS for short, a proactive load preservation system designed for power-intensive electrical networks, such as industrial facilities, generation plants, and distributed electrical networks. The objective of this presentation is to cover three topics. First, the need of a proactive preservation system. Second, the components and capabilities of the ETAP Intelligent Load Sharing solution, along with a software demo. And third, the value proposition. First, let's discuss why there is a need for a proactive preservation system. Load demand control becomes critical when the electrical network goes through transient conditions. Any system susceptible to large-scale disturbances such as faults, generator trips, and islanding. The longer the load sharing system waits to react to a disturbance, the more load there is that is required to be shed. The reasons for this are primarily the generator controls. Exciters and governors cannot act fast enough to these sudden requirements. The load sharing system needs to act faster even than the protection schemes, as they may cascade into further events. Without a protective load sharing scheme, your system is susceptible to loss of production and even blackouts. For these reasons, having a proactive predictive system will guarantee fast response under such events. Another factor to take into consideration is the location of the disturbance in the electrical network. The power requirements from the generators will be greater when a fault, for example, is closer to the generation bus than when it is far away in an MCC in the process plant. In addition, the disturbance type needs to be understood. A steam pressure drop, for example, may cause a partial decrease of generation, and you may need to shed only a small amount of load in comparison to one generator or two generator tripping. A proactive and intelligent system will determine what to shed considering locational and disturbance type factors. One other item to consider is the operation variations in the electrical network. This includes the load dynamics. Every system is unique, but what is common with all systems, the variation of loading. Sometimes it can be cyclic or it can be random. Depending on how much load there is in the system at the time of the disturbance will determine how the load shedding system will need to respond accordingly. The proactive system must also consider that if the operating load is closer to the capacity of the system is more susceptible to stability loss. Load variation of feeder must be considered when a breaker is selected for tripping. It makes a big difference to drop a feeder operating at 1 megawatt of load compared to when it is operating at 5 megawatts. This is very common in industrial networks, such as mines, where loads constantly move from location to location and can operate at random times, or in oil fields, where the loads depend greatly on the production of the well at that time. In utility systems, although load can be roughly predictive in a given day, it can suddenly change to unforeseen conditions, especially nowadays, where renewable and microgrids are being introduced, and when sudden weather conditions can change loading quickly. Other systems operating conditions to consider are network changes. The system topology is also important to know when performing load sharing and selecting which loads to drop. Breaker operations greatly affect the behavior of the power flows, as they change the impedance seen to the generations as well as the capacity of transferring power from point A to point B. Monitoring the operation of switching devices is a key factor for deciding which loads to drop, as they could be in a separate network if islanding occurs. Generation availability varies when performing load sharing. It is required to analyze how much generation we have available. This has a direct impact on the available generators to respond to sudden changes. A reliable and intelligent load sharing system can help you reduce such costs by reducing required spinning backup generation. Changes on your governor settings also impact the way the system responds. These settings must be taken into account when transient conditions occur. Other normal and abnormal operating conditions. At the time of the disturbance, it is also important to consider operating mode. Is the system connected to the grid or is it islanded? With an interconnected system, the load-sharing system needs to consider max and min import and export power contracts, as violating such limits can cause large penalties. After islanding or operating islanded, most of the time the system is operating with limited generation capacity. A reliable load-sharing system is even more critical as any imbalance of load and generator can develop into an unstable system. The bottom line is that with a different operating conditions, you get a different response. A proactive system will look at the existing conditions and prepare for disturbance events. So when they happen, the system is ready to respond accordingly. In summary, to perform proper load sharing, it is essential to account for the following parameters at the time of the disturbance: fast response, location of the disturbance, load dynamics, network changes, generation availability, normal and abnormal operating modes. Since it is impossible to detect, calculate, and respond considering all these parameters at the same time of the disturbance and respond within milliseconds, the only method to achieve this is through predicting the system response. Next, let's discover how ETAP ILS can achieve this goal. The ETAP ILS system solution is composed of three integrated solutions: load preservation engine, load restoration, load sharing validation. The load preservation engine monitors the electrical network and decides how much load to shed and which loads to shed. We refer to this as load preservation versus load shedding because its primary goal is to shed as little load as possible to maintain the stability of the system. The load restoration function, as the name implies, restores power to the available portion of the system while maintaining fault isolation without exceeding the capacity of the alternate power sources and routes. This is the engine that monitors the system and indicates to the operator when it is okay to restart shed loads. And load sharing validation, which is a very unique feature of ETAP. There is no other load sharing system that can allow the user to validate the response of their load sharing system before getting implemented or performing updates. The key of the ETAP Intelligent Load Sharing Load Preservation Engine is its understanding of the electrical network. With this knowledge, the load sharing system will be able to accurately predict system response and therefore be prepared for transient and steady-state disturbances. ETAP achieves this by using the electrical digital twin. The system model is represented in the ETAP ILS by the one-line diagram of the system. In fact, this model is the same model utilized by the electrical engineers on site and consultants performing system analysis. The main difference is that this model is now connected to the ETAP data acquisition system, collecting data from the field via IEC 61850, DMP3, or any other protocol. The intelligence of this predicted system response is that the online data provides the current conditions of the network, and the model provides us with the understanding of the system. This is due to the fact that the model contains a steady state and dynamic data of the components in the network. The governor and exciter settings that can be found in the model, the transformer ratings, as well as other components, gives a complete understanding of the network's behavior. Note that ETAP ILS is looking at the entire network instead of at a single parameter or component to make decisions. This is also another important factor in why ETAP ILS can perform optimization of the entire network. As you can see, it provides a clear picture of the system distribution as well as the data required to understand system response. An added benefit for operators and engineers is that they are able to visualize the network distribution. In addition, ETAP ILS utilizes the following parameters to optimize the loads to shed selection: load priorities, hardware and process interlocks, selection of the best combination of loads to shed in order to ETAP ILS to select the optimal loads to shed. It utilizes user-defined load priorities. In addition, it is important to understand process behavior. In many cases, dropping one load can cause other loads to trip. hardware and process interlocks must be incorporated and considered. ETAP ILS provides an easy-to-use user interface to input this information. In the ETAP ILS load control editor, we can add or remove loads and update priorities and interlocks easily without the need to reprogram controllers or relays. By simply manipulating the ILS default load priorities and grouping loads under the interlock, you can achieve this goal. ETAP ILS also provides flexibility of operation with these features: a friendly user interface, monitoring and spinning reserve and system frequency, update logic without PLC programming, unlimited load sharing schedules, alarm and logging and load sharing events. ETAP ILS provides a friendly interface to monitor the load sharing system. For each contingency being evaluated by ILS, the operator or engineer can monitor critical parameters such as the spinning reserve, required load to shed, and actual load that will be shed if that contingency were to occur. ETAP ILS logic is available for engineers who've been granted the right permissions to perform modifications without going into the relays or PLCs to do so. An unlimited number of schedules can be set up and uploaded within the ILS system without the need to bring the system down. All we need to do is go to the server and update it and select the new schedule. Another important capability is the management of multiple islanded and interconnected systems. The ETAP ILS will shed loads based on system connectivity. One of the most powerful features in ILS is the automatic handling of load to shed based on how the network is interconnected. The system can identify an unlimited number of islands and shed loads accordingly. Notice that the ILS trigger monitor demonstrates one system index in both triggers and loads, the subsystems. This index indicates in which subsystem the loads and triggers are located. If the location in the network islands, a new subsystem index is assigned to the new island. It is important to understand that it is done automatically, without the need for any programming. Since it is based on the ETAP model, ETAP ILS understands the topology and performs the assignment of subsystems automatically. In an under-frequency system, it is almost impossible to set up system islands. In a PLC-based system, it can take hundreds of conditions to identify islands, and even an industrial network, imagine the testing and debugging time and effort. With ETAP island setup, identification is automatic. Now let's look at the ETAP ILS response time. Under transient conditions, the operation is within 20 milliseconds on average. In some systems, 6 milliseconds response time has been achieved. For a steady-state operation, the response time is controlled and configurable depending on the disturbance type and location. Note that the steady-state operation refers to conditions such as excess power demand, equipment overload, sequential process shutdowns. Also note that ILS is not limited to electrical disturbances. ETAP ILS can respond to mechanical and electrical disturbances such as generator breaker trips, utility main breaker trips, fuel availability, process alarms, faults in the system, spinning reserve availability, user customizable triggers. In conclusion, the load preservation module is a very powerful yet easy-to-use application within ILS to optimize load sharing, identify islands, and respond to electrical and non-electrical disturbances. Now let's look at the load restoration. ETAP's load restoration monitors electrical and non-electrical conditions to determine when loads can be restored and when they cannot. It also has the capability of automatically starting loads when safety permits it. Load restoration comes with load inhibition, which becomes active until loads can be restarted safely. The HMI screens will indicate to the operator when it is safe to start the load. The program utilizes load restoration logic and priorities to determine which loads can be started and when. It uses a logical load sequencer to restart the process. It also has an open logic editor for customizing the logic. One great feature of ETAP ILS is the capability to perform its own load-sharing validation. ETAP ILS is a complete suite of modules that allows the user to start from simulation and smoothly move into implementation. After configuring the ILS system, the user can proceed to simulate the triggers in the ILS simulator. The ILS simulator is a duplicate of the real-time applications, with the exception that it can take data from the load flow module and from user-defined data. The next step is to evaluate the actions by viewing them in the ILS trigger monitor. Then they can be analyzed dynamically using the transient stability calculations. Once it is approved, the logic and priority tables can be updated to the real-time load-sharing system. The load-sharing system supports the engineer by validating the results from ILS before implementing this within the network. It can utilize real-time data as well as user-defined and simulated data. All the modules within ETAP are available to perform such validations, such as load flow, transient stability, motor acceleration, and more. The validation process can consist of simulating and analyzing loss of generation, under frequency, mechanical failures, steam pressure decays, overloads, and other conditions leading to load shed. One last thing to remember about ETAP ILS, the system is hardware manufacturer independent. It integrates with third-party LMS, PMS, and SCADA systems, utilizes the latest communication protocols, integrates into existing infrastructures with minimum investment. No need to replace hardware in most cases. It is compatible with high availability architectures as well as with hardware, software, and communication redundancy. Now let's look at the industries that can benefit from ETAP ILS. The industries that are in need of intelligent load-sharing systems are systems requiring transient and steady-state control of load generation balance, such as those which are operating with limited generation, are operating critical safety-related loads. ETAP has implemented ILS in oil and gas fields, city distribution networks, transmission systems, water treatment plants, cement plants, steel plants, mines, oil refineries, chemical plants, manufacturing facilities, data centers, offshore platforms, and more. Now let's talk about the benefits. Let's go directly to the bottom line, cost of savings. Cost savings can be realized by ETAP ILS as follows. First, protection against production losses. Sharing the correct amount of load at the right time under the correct disturbance can definitely save you some money. For example, Lafarge Holcim Cement in El Salvador dropped their production losses due to critical kiln trips by a staggering 95%. Combined with the fact that a minimum investment in time and money was needed to implement the solution. And the return of investment was realized in just 3 months. Second, lower cost for operation. Having an intelligent and reliable system has its payback. As an example, we have Amman Mineral. Amman Mineral has estimated an ongoing savings of about $5 million plus per year by reducing its diesel fuel consumption for backup generation and spinning reserve. The ETAP ILS system has operated at the mine for over 16 years, bringing reliability and stability to the grid without a vast reduction of need for diesel generator backup. The return of investment on such a system was almost immediate. Let's not forget that by avoiding blackouts of their primary mills, Amman Mineral is saving another $2.5 million in production loss avoidance. And third, let's not forget the environment and safety. Overloading of generators can cause them to run inefficiently and also produce excessive CO2 emissions. Reducing the load in emergency conditions quickly and safely can avoid heavy fines or penalties for pollution. This cost savings is a case of B. Brown Medical Manufacturer in Irvine, California. In conclusion, there is no other solution in the market that can provide you with the ease of use, power features, fast response, and fast ROI like ETAP ILS. Thank you for joining in this presentation. Please let us know if you have any questions.